Good morning, myself Yarashan from IARE Institute of Aeronautical Engineering. This is my topic efficient graph search. The topic under data search. Introduction to the graph search. Graph search algorithm explore nodes and edges in graphs to locate the target nodes or path. They are fundamental in AI, pathfinding network routines, and a knowledge representation system. Efficiency in a measured by time and space complexity, often expressed using big O notation. Such stages vary based on whether the graph is directed, undirected, weighted or unweighted. Application include GPS navigation, social network analysis, and game AI decision making. Graph representation agency agency list. Agency list represent a graph as an array of linked lists where each complex cooperation uh, corpor- co- co-represented to the vertex. Each list contains all vertices adjacent to the vertex at the index, enabling efficient travelers. Space complexity in O, V plus E, where V is vertices and E is edges, optimal for spherical graphs. Graph lookup takes time, making it slowly than adjacency matrix for density query. Graph represented adjacency matrix. Adjacency matrix is a V into V 2D array where entry, incident, and edges between vertex I and J. For weighted graph, the matrix store each edge weight 0 or infinity denoted no connected connection. Space complexity in OV square, making it inefficient for large space graph. Matrix operation enable algebraic graph analysis useful in spatial graph theory and ML. Breather first search BFS algorithm alg- algorithm overview. BFS explore nodes level by level using a QE starting from a source vertex. In generally, in the shortest path in unweighted graph due to its level order travelers, the time complexity is O, o into V plus E. Visiting each vertex and edges once in a connected component. Space complexity is OV due to QE storing fronting nodes at the widget level. BFS implementation and piezo code. Initialized as a QE mark the source nodes as visited and in QE it. While the QE not empty, in the QE node and process its inverted neighborhood. For each neighborhood mark is vertices in NQE to be continued level visited explain. Depth first Depth first search DFS algorithm overview. DFS explores as a far possible along each branch before bracketing using a staff or uh, recursion. It does not Gary started path, but if thinking for circle Deletion and topical topological sorting. Time complexity. Visiting each vertex edge once a connecting component. Space complexity due to resurfacing stack defects in the worst case. DFS implementation and residue structure. Starts at the source node, mark it visit, and result visit at all unweighted adjacent node. Use a use a visited array are set to prevent living nodes and infinite loops in cyclic graph. Bracketing occurs where a node has no unweighted neighbor return to the previous cell. The DFS can be implemented iteratively using a exploit stacks to sim- simulate regions. regions. Uniform Uniform cost search (UCF) principle and motivation. UCF UCS expand BFS to weighted graph by expanding the lead cost node first using a proximity QE. It optimized for finding the lower cost path where edge costs are not negative. The cost function represents the cumulative path cost from the search node to node end. USC algorithm and complexity analysis. Initialize the proximity QE with the start node having cost G start is equal to 0. Extend the node with a minimum, expand its circles and insert and update their cost if improved. If it node is revived with low cost, update its priority in the QE. Time complexity using binary if due to priority QE operation. Space complexity for storing nodes in the frontier and explored set. A set, A plus set. A combining USC with various function H into N to estimate cost from node N to goal. The elevator function f of n is equal to g of n plus h of n. Build search towards a goal efficient. A search. Design an example. In a grid-based pathfinding, mathematic distance is used for 4-directional movement. Example: pattern database pre-compute heuristic value for complex state space like in 15 puzzle. Compression of search algorithm. BFS finds shortest path in unweighted graph with time and space. DFS use less memory but may not find the shortest path, useful for extensive explanation. UCF Garnity optimize path in weighted graph with non-negative edges in time. A star improves UCS efficiency using heuristic, uh, reducing the search space significantly. Choice depends on a graph type, edge weight needed for optimally and available heuristic information. Bidirectional search concept and efficiency. Bidirectional search runs two simulation search, one forward from start and one backward from goal. Uh, Interactive Depending DFS, IDDFS combine DFS space efficiency with BFS completeness by performing depth limited DFS interactive in it increases depth limit from 0 upward until the goal is found, ensuring shortest path in unweighted graph. Time complexity same as BFS, but space complexity in O much lower. Performance optimization and engineering trade-off. Memory efficient representation. Reduce overhead in large-scale graph. Parallel BFS or DFS. Implementation leverage multiple core processor for fast travelers in distributed system. It turns into A plus balanced uh, ad- admittedly to complementation overhead for real-time performance. Caching frequently accelerate path, improve response time in dynamic environment like terrific network. Hyperic approach. Optimize grid based A star by skipping semantic path. Thank you.